Hello everyone, my name is Paulo Mendes and I'm going to present a brief review of the main fatigue design criteria presented in the literature for offshore wind turbine structures. It is crucial to understand the fatigue phenomenon and identify as soon as possible how it affects structures, considering that offshore structures are constantly submitted to cyclic loading and corrosive attacks, provoking progressive and localized structural damage and the growth of cracks. Offshore structures are divided into fixed and floating structures, and the determination of which type of structure fits the best depends in various factors as water depth, roll, and functionality. Here, on the left side, it's possible to observe an example of fixed type of offshore structures, and here, on the right side, possible floating type of structures. The design of offshore structures is based on the conditions and the environmental aspects in which the structure is submitted. For the static analysis, an offshore structure can be submitted to permanent loads as dead weight and equipments, gravity loads, live loads, and hydrostatic loads. Dynamic loads are generally originated by environmental loads, wind loads, wave loads, current loads, ice loads, and other environmental loads. Environmental loads are studied with more detail since the evolution of cracks in these structures are due to them. In this work, wind loads and wave loads are studied with more detail. Wind-induced loads are often treated as time invariant and wind acts in a direction normal to the surface of the structure. Usually, to represent the wind force, the equation used is the one here. Waves. Due to the random nature of the ocean waves, in weight, shape, direction, length, and speed of the propagation, the state of the sea is best described in a random wave model. The linear model, developed by A.M.P, is the most simple theory of waves and currently the most precise for waves of small amplitude. For the A.M.P wave theory, the waves have sinusoidal shapes, where the free surface profile is described by the formula below. Selecting the wave theory applicable to an offshore structure model is an essential step in a hydrodynamic analysis. In cases where the wave amplitude is not small or for high values of wave inclination where linear theories do not reach an adequate degree of precision, nonlinear theories are adopted as, for example, the Stokes wave theory. Stokes theory assumes that any variation in the x direction can be represented by the Fourier series, which can be written as disturbance expansions that increase with the wave weight. Using this series, any order of approximation for Stokes theory can be obtained, and this one used in the first order is identical to a linear wave. For example, the wave surface profile in second order theory can be obtained from this equation. Morrison's load formula is applied when the wave length is 5 times bigger than the cross-sectional dimension of the member. For fixed structures in waves and currents, the hydrodynamic force is calculated according to the Morrison's load equation. Different approaches can be used in the fatigue analysis, but the decision of which method suits better depends on which structural details need to be considered. The damage accumulation law of Baumgartner-Minor is a common method to estimate the fatigue life of structures submitted to a historic of variable loads based on a series of fatigue stresses with constant amplitudes. Here, it's presented the Baumgartner-Minor rule. Below, here are defined the variables presented in this equation. The SN curves found in the technical recommendation are expressed in a big logarithmic scale in which the fatigue strength is given by the number of cycles until failure, in function with the stress range. The SN curve can be obtained through this equation. Also, the variables are defined below. In this slide are presented the SN curves for tubular joints in aero environment, seawater with cathodic protection, and free corrosion from the DNVGL standard. Fatigue evaluation in tubular joints is essential to the design of offshore structures. To the fatigue damage evaluation, the Weibull distribution of two parameters is used to analyze the distribution of stresses around tubular joints. This methodology also uses Baumgartner-Minor rule allied to the SN curves. For continuous stress spectrum cases, the long-term stress range distribution might be defined applying the Weibull distributions for the different load conditions and can be estimated using the following equation. The variables annexed to this method are defined here. Due to the excessive sensitivity of the estimated fatigue damage of the Weibull parameters, a spectral fatigue assessment becomes more popular for offshore structural analysis. The spectral fatigue analysis method recognizes the stochastic nature of the marine environment to which the offshore structures are inserted. The spectral fatigue calculation starts from the assumption that there is a relationship between the direction and frequency of the wave and the voltage response at a specific location. When the direction of the wave is considered in the definition of sea states, using the Rayleigh distribution, the accumulated damage for all sea states can be calculated using the equation below. The variables are defined here. In welded joints, the fatigue strength is estimated through cyclic stress in the point of interest. There are several methods and approaches to determine the SN curves: nominal, notch, and hotspot approach. The nominal stress can be determined using elemental theories for structural mechanics based on a linear elastic behavior. Hotspot is defined as the region in the joint where fatigue cracks are more susceptible to appear due to cyclic loading, meaning that hotspot stress is the value of the stress in the surface of the hotspot. According to the NVGR recommendation, notch stresses must be considered in special cases in which it is hard to evaluate with assurance the fatigue strength using other methods. Radaj demonstrated that the notch stress components can be divided from linear stress, membrane stress, bending stress, and non-linear stress part. The stress distribution through the thickness of the weld plate and its components are shown below. In tubular welded joints, when geometries discontinuities are considered, consequently there are changes in the stress field of these elements. This way, with higher points of stress, the structure is more suitable to fail. Therefore, the stress concentration factor is used to evaluate this concentration ratio and is defined usually as the ratio between the hotspot stress and the nominal stress. The NVGL recommendations present different parametric equations to obtain the stress concentration factor based on Eftimius's researches, calculated in different points of the joint connection, taking into consideration different geometrical parameters. The stress concentration factor can be obtained analytically, numerically using the definite element method, and experimentally. The fracture mechanics approaches assume that all structural elements have defects and cracks, and consequently, the design is based on the tolerance to these defects. There are three basic modes of fracture. Mode 1 is the tensile opening mode and is characterized by the separation of crack faces in the direction perpendicular to the crack plane. Mode 2 is in the in-plane shear mode and is the mode in which the crack faces are sheared in the direction parallel to the crack front face. Mode 3 is a transverse shear mode, and similarly to mode 2, in this mode the crack faces are sheared, but this time in the direction perpendicular to the crack front face. Here are represented the modes. It is assumed that compression doesn't influence crack propagation, but since welded joints contain residual stresses, all the stress spectrums must be considered. The crack propagation can be divided into three stages. The first is characterized by considerable low crack growth rates, and in this region can be identified a value, known as threshold, above which there is no crack growth. The second stage is the region known as Paris region, because the crack growth as function of stress intensity can be defined by the following expression, which was proposed by Paul Paris. The stress intensity factor can be expressed as displayed here, where this variable is the nominal stress on the normal member to the crack, G is the factor depending on the member geometry, weld and crack geometry, and A is the depth of the crack. The third phase of the crack propagation is the last phase and is characterized by an unstable crack growth until the total failure. The availability of accurate fatigue propagation laws is the key for a reliable fatigue life prediction of mechanical components or structural details. The most common use of the fracture mechanics based on fatigue crack propagation relation consists in residual fatigue life assessment of mechanical components or structural details containing initial known defects acting like cracks. This can be accomplished integrating the crack propagation law according to the following expression. An offshore wind turbine can be exposed to various factors that carry fatigue damage. The phenomenon of fatigue is one of the main causes to structural failure, which consists in the loss of strength due to the appearance of cracks in an element subjected to cyclic or dynamic loading. Understanding the fatigue design phases, criteria, and existing approaches is therefore of extreme importance for an effective and clear design of an offshore wind turbine. I hope the presentation was clear enough. Any questions regarding the presentation, feel free to ask, and thanks for your time.